Well, if you know me, maybe you're not surprised to see that my talk has the first word AutoGraphiX, because AutoGraphiX is a software which I developed for now 25 years. And unfortunately, I forget. When I pass the 25 years, I forget to write a special paper. I will wait for 30 years now. Of course, from all this time, I didn't just keep the software running and wait. So, of course, there have been lots and lots of developments. Just this morning, I double-checked one thing, and I found that some results which we have really huge difficulties to find, I think 5 years ago, could now be solved in a few minutes. So it seems that everything is going smoothly. So from time to time, I come and try to update people who eventually are interested in the software to know what's new. So in this talk, I will have two parts. The first part will be kind of theoretical, based on some measures of distances in networks. I will just explain some concepts because it's well, it's of interest to me nowadays, and I try to study in this area. So I work on it. And the second thing is that, of course, when I work on some topic, I try to ensure that AGX can follow me. So I update the software to be able to study these problems. And I would take this opportunity to ask people if you are trying to study some problems and would like some insight from the computer. I mean, some problems in graph theory. I cannot solve all problems. Please do not hesitate to contact me. It will be a pleasure for me to try to improve the software, and it's the only way for me to know how to improve the software. Otherwise, I will just work on stupid things. Now, how can I change the slide? Well, well, I will start by just some basic information. I guess everybody knows about that already, but still, it's a good idea to come back on that. So, what is a graph? First thing, a graph is a mathematical object which is made of nodes and arcs, and actually, it's really used in different fields. Mainly, some people claim that the graph came from chemistry. Well, I remember a chemist who came in GERAD some years ago, and he was stating that graphs are coming from chemistry. Now, I'm not sure it's true, but everybody can find the graph in their field, so it's easy to say that we are the first. Anyway, it was quite used in chemistry. The impact, well, if you study graphs from the data analysis point of view, it's quite interesting. Because usually when you have data, what you have is a set of observations, say, which are described by a set of variables. Okay, so we have what we call a table of data. What is really special in the context of graphs is that what we have some observations, some objects. But they are not described in a multidimensional space. They are described by their relation to each other. So it's completely different nature. Now, still, we can use graphs to represent some classical data, especially when the data is sparse. Because in this case, we forget the zeros, and we have what we call a bipartite graph, where we have some nodes which correspond to the observations, and we can have some other nodes which corresponds to the variables, and eventually we have some weight if the value is non-zero, if it does exist. So in some cases, we can do both. Well, okay, it's something which is widely used. And what is funny is that people like graphs because it's easy to draw and it's easy to get some intuition about what we are saying. Like I can draw a graph and say, well, what about this property? And try to build another one. And people, well, we can interact. We can just have a figure, and it does help intuition quite a lot. What is really funny is that nowadays we have lots of graphs, but they are in the computers, mainly they are in database, and they are so large that we cannot visualize them anymore. So it's funny, we have some tool which people like because it's easy to visualize, but we cannot visualize them. If you have, I don't know, if you try to work on a graph on 300,000 nodes, I did many times. I didn't even try to draw that. You know, it's just an object which is in your computer, and you have to use some measures to figure out what it looks like. And the good thing is that we used to work on graphs from years and years, and we developed lots of measures. So we can get some intuition because of our prior knowledge. For instance, when I started, I worked in chemistry. And the graphs I used had, say, 10 to 20 nodes at most. So it's easier. In the case of AutoGraphiX, I will not work on large graphs, but what we are doing, we are not studying the graph as such. We are studying the measures which help understanding the graph, which is what I just told. Okay. Now, if you know a little about AutoGraphiX, or if you don't, I will tell you. The very first version was based on what we call an invariant. An invariant is a function such that you give a graph and it gives a number, okay? And if you draw the same graph differently, I mean, if you move the nodes or things like that, it will not change the number. If you label the nodes differently, like you change the first for the second, so you change just the names, it will give the same number. So it was quite convenient. And I was just optimizing to maximize or minimize some function of invariance. Then I realized that it may be interesting to study nodes as well. And especially in social networks, we are interested in centrality measures, for instance, or in telecommunication network, we are interested in centrality as well, just because it corresponds to some hubs which could be critical. So in different fields, we are interested in the nodes in the network and not the network as a whole. So we decided to change a little the way the software is working. Some common tasks we are doing so by using vertices. Well, we can try to identify important actors, like influent actors in social networks. Well, influencers. Did you hear about that? Maybe you did. That's what we call centrality analysis. We can try to find some groups. Like usually in marketing, we talk about segmentation, market segmentation. We can talk about clusters in data analysis more generally. But in the context of network, for some historical reasons, we call them communities. But it's the same idea. Except in data analysis, when you make clusters, you try to find sets of objects which are similar to each other and try to ensure that different objects are in different clusters. Okay, the two concepts for building clusters. In the case of network, it's quite difficult to say that these two nodes are similar or not. But you can say that they are close in the sense that you have paths between them or something. So we use some slightly different ways to represent the same concept. Now, what is interesting as well, studying the way information does spread in the network. This is something which I do not tackle with AutoGraphiX right now. I plan to do it in the future, but there are lots of challenges. Okay, so this is for the background. Now I will talk a little about distances. When I told to some of my colleagues that I teach a course in complex networks that some of you are attending right now, so I said that I have 2 lectures dedicated to distances. When I said that to some of my colleagues, they just laughed. They said, 2 lectures for distances? What are you doing? Examples? Well, but 2 lectures means 6 hours, so it's quite a lot. The problem is actually when we think of distances in a network, we always think of shortest path. Okay, if I say a graph, what is the distance between 2 nodes? Shortest path. Okay, shortest path, why not? It's one possibility. I would say, if you're interested in, say, telecommunication network, of course, you will search for the shortest path for 2 different reasons. The first, because you want the signal to reach the goal quickly. So try to avoid useless hubs. And the second reason is that if everybody sends a message through a path which is not the shortest, you will overload the network. Because the same information is repeated many more times, so on the whole network, it's not efficient. So in this case, yes, the shortest path is a good idea. In transportation, the shortest path is a good idea. Of course, you want to be fast, you want to save on gas, that's okay. We will use the shortest path. How can we be sure when some information spread in a social network? How can you be sure it will follow the shortest path? Why should it follow the shortest path? We don't know. Sometimes it's random. And the shortest path may not give a good idea on the connectivity inside the network. Also, what is interesting, a network could represent lots of different situations. I would say, I don't know exactly what to use. It may be some physical network, like power distribution network, like telecommunication network. It could be some physical network. But it may also be something which is more abstract, like a social network. Can you give me the list of your friends right now? No. Usually you don't. It's if I say, do you know this guy? Oh, yes. Oh, I didn't meet him for 5 years. I didn't think of this guy anymore. What's going on? So this kind of network is slightly more difficult to really modelize. But there are also some really abstract networks. For instance, if I'm interested in the language, then we have some words, but these words are related. For instance, if I talk about a car and I talk about a bus, there is a link between both of them because they are all very high cost. Now, if I talk about a car and a wheel, there is a link between because the wheel is on the car. So you can have different ways for words to be related. They are talking about the same thing, for instance. So for this reason, we can build what we call a semantic network, which is a network of words with link between two words if they are related in the sense that their meaning has some similarity or some common point. What does it mean to compute the shortest path in a semantic network? Nothing. It just doesn't make sense. We have nothing which is running on such a network. You know, eventually, when an information spreads in a social network, you can still find a link that is okay. A link makes a sense. A path have a sense. But if you have a semantic network, even a path that does not represent anything concrete. And in this case, I'm not sure using the shortest path is a good way to represent distances in such a network. I mean, you can have two worlds which have lots of common neighbors. They will probably be closer than two worlds which have just one common neighbor. Okay? Except if you compute the shortest path, it's the same. So we see that we have different ways to measure the shortest path. I will talk today, well, so maybe you know already about this geodesic distance with what we usually call the shortest path. I will not present the Gilles algorithm here, but we all know about it. I'll talk about Jacquard distance. And so that's a measure which will more fit for the case of semantic networks, for instance. And then I will talk about the one I prefer, resistance distance. One funny thing is that this concept was proposed in 1993. Well, 89, depending on how we go, because there are two papers on that, slightly different. But resistance as such is 93. And I will talk about random walk distance. Well, just because it's related to the previous one and it's some work that we did. So usually we want to make advertising on our own work. So I will talk about this. Well, I could talk about slightly more, but I keep some extra for my students in my class. Okay, let's talk about the geodesic distance. I will not spend a lot of time here because I want to keep some time at the end of the presentation to talk about high edges and how we try to handle distances in the software. Okay, so DIG is the minimum number of edges in connected subgraph containing the nodes I and J, which is actually the way to describe the shortest path. Basically, You take a path and you ensure that it's as short as possible, and you count the number of edges that you have to go from one node to another one, and this will be the shortest path, the length of this shortest path. I can give you an example here. So you have one network, well, we have two nodes here, which are at distance 3. Okay, well, we have another network there, which has the same, between these two nodes, we have exactly the same geodesic distance. And again, it is 3, but we can see that actually the other nodes are not connected so much. And perhaps in practice, depending on what application we are talking about, perhaps we should not consider these two paths with the same distance. Depending on what we are doing, maybe this network is more efficient. Well, if you're thinking of telecommunication, I guess it's clear for you that this one is better. Except if you have to pay to build the network, you will prefer this one. And that's actually quite interesting. I realized, well, when discussing with my colleagues, especially from UFES, I realized that one requirement for telecommunication is that it has to be bi-connected, so that if an edge fails, you still have a backup path. So it's a condition. But in practice, and we have this for telecommunication, we have this as well for power distribution. But in practice, it's very rare because it's so expensive. And sometimes we say, okay, we would like you to have a backup path for your electricity, but you know where you're living, it will be too expensive. So you just have one path and just cross the fingers not to have a problem on that. Okay, that's in practice what happens. Okay, now what could we say about this? And it was first thing to realize that actually this shortest path is widely used, but it's not so good. It only relies on few vertices. You only take the vertices on the shortest path and you give the number which characterize the relation between the two. So you have very few. The geodesic distance is sensitive to small number of modifications in the graph. So it's not robust. If you change a few things, the geodesic distance will change. So it's not robust, but it is insensitive to others. So it may happen that you change the network and some measures will not change. By the way, if you just look at, take a network and look at the different values which you may have as geodesic distance, actually it's bounded by the maximum, which is what we call the diameter. And the minimum usually is, well, it's 1 when the two nodes are adjacent. And you look, the number of different values is usually small. Just to give an idea, did you hear about 6 degrees of separation? So it means that when you have two different people in the world and you want to find a path between these two people by just the relation, I know this person. So you take one person, knows this person, and you can go from anybody to anybody, usually in about six steps. It's what it says. So it means that all the distances you may have is 1, 2, 3, 4, 5, 6, just few. So it's quite degenerate. It's not robust. Well, it's not necessarily the best method in all cases. I will just now do a parenthesis. This one is it on time? No. Oh, okay.
More or less.
Yeah. I will do a parenthesis because I realized recently some interesting things. In 1999, which tells you that I'm old, we wrote a paper about Osoya polynomial and its palindromicity. So I will just give you some basic hints, just because it's really fun, really interesting. What is the Osoya polynomial? Well, if you take a network and compute the distances between pairs of nodes, you will have a certain number of pairs of nodes at distance 0. Well, actually, this is the number of nodes. Each node is at distance 0 from itself and not from the others. Now, it's still, of course, geodesic distance. Now you have a number of nodes at distance 1, which is the number of edges. That's still okay. And then you have a number of pairs of nodes which are at distance 2, 3, 4, and so on. And you have a maximum, which is the diameter. Okay. Now let's build, well, what we call a polynomial, or we can view it. In this case, it's more convenient to view it as a vector. So we have a vector here of all distances. Okay. And well, mathematicians like very, very interesting and very important questions. So their question was, is it possible to find a graph which has such a vector, which is palindromic? What does it mean? It means the first term is equal to the last one, the second to the previous from the last, and so on and so forth. Of course, if you run the computer software, you will easily find lots of graphs which have palindromic Ossoya polynomial. Now, the question is a little more complicated when we are interested in trees. And when Goodman came to Montreal and asked about this problem, it was still open if there exists some trees with palindromic Ossoya polynomial. So we used the software. And for this, we had to define a function to minimize. And this function was very simply, you take the difference between this term and this term in absolute value, plus the difference between this term and this term, and so on. So you take the terms which should match, make the difference, continue absolute value, and do the summation on your measure. So you get a distance to palindromicity, which is what we called it Z of t. Then run the software, minimize this, find the tree which does minimize this. In I would say few minutes. Nowadays, it would take a few minutes, but perhaps at this time it was a few hours. We get a lot of graphs of trees which had a palindromic Ossoya polynomial. So this conjecture was disproved. Then what happened is that in all cases, what we found is that the diameter was actually even, which means the number of terms we have here is odd, which means we have one guy in the middle, which is free. So I would say this was the easy case. Now we fix the constraint that the diameter has to be odd, in which case each term has to match another one. Okay? Run the software, you will not guess what we found. We found that we tried different values of n, so number of nodes, and we realized that this number, Z of t, was increasing in a very, very regular way. And actually, it was the lower bound, what we found was the scaling of n divided by 2. So it means if you take a tree on, say, 20 nodes, you want to minimize Z of t, so the distance to palindromicity on the set of trees with 20 nodes. And if you ask the diameter to be odd, you will not get something which is below 10. It's quite surprising. Do you have an idea how to prove that? Of course, when we had this, we thought, oh, this is about impossible to prove. But let's propose it as a conjecture, and maybe some people later will try to work on that. I personally took a lot of time to try to understand what's happening. You know, trees are interesting because you just have one path between any pair of nodes. So you can have some structure, you have lots of things. I spent some time, but I was not smart enough, I didn't find it. You know what? Some people have proved that. In 2022, there was a paper in March proving this conjecture. I was really surprised from that. I read the proof, and it's 3 lines. And it's just, we cannot imagine how smart it is. Well, you will imagine when I will tell you. And more than what we did, they said, okay, a tree is a bipartite graph, and our proof works for all bipartite graphs, not only trees. And the idea is very simple. If you have a bipartite graph, and you say that two nodes are at an odd distance, it means that you start from the set A and you will finish on the set B, okay? Because it's bipartite. So you go from one side to the other side, it will be one step. If you come back, you will have two. If you go forth, you have three. So if you have an even number, you come from one side, come back to the same side. And if you have an odd number, you come from one side and go to the other one. And they say when you make this, so you take these pairs matching, each time you want to match a distance which corresponds to both sides, which with another distance which corresponds to the same side. Because this is even, this is odd. This is, no, this is even, this is odd. This is odd, this is even. So, and these people said, so if we make the summation of all the pairs which appear in an odd distance, it will correspond to the number of nodes in one side multiplied by the number of nodes in the other side. And if you take the pairs on the same side, well, you make the combination of two nodes in A, for instance, in one group, and combination of two nodes in the other group, and you will have the summation. So what they do, very simply, they make the summation of the odd values here, and they say it will correspond to this combinatorial measure. And for the even value, they do the same, and they have a combinatorial measure. They make the difference, and they find setting of n divided by 2. So, well, I thought this was really, when I read this paper, I found it really amazing. Actually, the proof is quite simple, and that's what I like. You know, you have something which is really complicated, nobody succeeded. Well, you know, it was open for 25 years. Almost like 23 years. So it was open for a long time. And so the guy come, it's a very smart idea, make a proof in 3 lines. Okay. So we had this conjecture, and it was proved in March in 2020. You can read the details there, but it's really simple. Now, I will talk about some other distances, but I will try to not waste so much time. Here, my formula are not really nice, but I will just explain the concept. Do you know the Jacquard distance? When I read your face, it says no, and when I read when you say explicitly, it says no as well. So I will just explain. Jacquard distance was actually proposed by a guy who's named Jacquard. Well, okay, that's not the most important. It was at the beginning of the 20th century. I think it's 1901 or something like this. And the way to compute the distance is based on a representation of objects by a set of attributes. Okay, so if you have one object, it's represented by a set of attributes. You have another one, a set of attributes, and they may have some common attributes or not. And you say if these two objects are sharing the most part of their attributes, they will be closer. And if they share few of their attributes, they will be at larger distance. So the way to build a measure is just to count how many attributes are involved. Say between these two objects, say you have 20 attributes. How many of these are in common? And then you make a ratio. If the ratio is about 1, it means they have almost all their attributes are shared with the other one, which means they're close. And if the ratio is about 0, it means that they are described by different attributes, which actually means the distance is larger. So you compute what we call the Jacquard index, which is the ratio I just explained. And then the distance is computed by, well, this ratio is between 0 and 1, of course. And the distance is 1 minus the Jacquard index. That's very simple. Again, I will not waste your time for that. But this measure is quite interesting, especially I was talking about, you remember concept graphs or semantic graphs, well, this is a case where it should be really interesting. The only bad thing, if you apply it in a network, as soon as two nodes do not have any common neighbor, they will have a distance one. Okay? So you start from one node, you can have some closed nodes, and then as some step, you have distance one, and maybe all the others are distance one. So what does it mean? It means that, again, this is really degenerate. So if as soon as the geodesic distance is larger than 2, the Jacquard index is, distance is equal to 1. So you lose a lot of information. Again, from this, we built a measure which uses both geodesic distance and the concept of the Jacquard distance. And we built a measure which is really more informative in the general context of networks. So we have a single measure that does fit for all these cases. But I will not go in details for that. I will just spend some minutes talking about the resistance distance, but I don't want, again, if you're interested, take my course. No, it's a joke, but you can look at the paper, and it's really interesting. And the way they proceeded, well, it was a long time ago, like 93, it means what, 30 years ago. The idea was you take your network and you consider each arc, or each edge, sorry, as a resistance of 1 ohm. Okay? And then from your basic electricity law that you remember from when long time ago when you studied electricity, I don't know how much you did on that, but I remember some formula from that. You can compute what we call an equivalent resistance. So basically it means if you take your network, so say you want to compute the distance between A and E here, you compute this, you make this network, you suppose that each arc corresponds to a resistance of 1 ohm, and then you induce a current of 1 ampere from A, which will be leaving from E. So you make a flow in your network in this way. And the idea is to compute the difference of potential between A and E to identify what is the resistance of this whole thing. Okay? There are some technical aspects there, but this is the concept. Now, what we are using in practice to compute this resistance, we are using the current, which is running on each arc. Okay? We are using this to compute the resistance. Well, I will not go to the equations here, but what I would like to stress, if you run 1 amp, the current of 1 amp here, it will be split in these arcs. And the summation of these 3 currents will be equal to 1 by flow conservation. So you have some rules like this. Like you have a current which will be inversely proportional to the resistance, which is some basic law, and you have flow conservation. And what is really interesting is that from even before this time, it was shown that this concept of electricity could fit also for random walks. Like, suppose you have a message which starts from A, and you know that it has reached the target E, the probability that it does use such a path will be described by the exact same formula as the one from which you compute the current. Okay, so that's quite interesting. And when you read papers even from this time, they will make the relation between random walk and electricity properties. Again, a funny thing, in 2018, well, I think we did the work a little before, When I was, especially, I talk about this because I was in Vitoria at that time, and we conclude that. We realized that actually this relation is well known, but the resistance distance does not tell you about the expected length of a random walk. I mean, if you have some probability to take some path, you can compute with some probability you have a length, and then you can compute an expected length of a random walk between the two nodes. And we found that it was not given nowhere. So we built it, we made how to compute that. It's actually very easy. And so we proposed a paper in 2018. That's quite a lot. You know, it was invented in 93 and nobody did this last step. So it's just to tell about distances. Now, let's, if you're interested in how to compute it, I would say you can look at the papers or you can ask me after the course because I'm not sure I will have time right now. Okay, that's just what I just went to explain. Just I will move on to some properties, just because it has may have some interest. So you have omega, which is the resistance between two nodes. You have the geodesic distance, and then you have the random walk distance. So we have now three measures of distances. And what is really interesting, if you have a tree, which means you have only one path for each pair of nodes, all these three measures are exactly the same value. But if you add some cycles, what happens? Well, if you add some cycles, so you had more edges, then the resistance will decrease, which is what you expect, because if you have more paths, the resistance will decrease. And the expected length will increase. Because if you have more paths, you can get lost more easily. We can see that in this way. If you just have one path, you will follow this path. If you have more than one, you can, with some probability, take one which is longer than the shortest path. So the expected length of a random walk is necessarily larger than the shortest path. Okay, and the resistance is always smaller than the shortest path, except if there is just one path. So we have this inequality. And we decided to look at this a little more in details. And of course, it's always easier to work on one value per graph. So we have the summation of the geodesic distance, which is well known as the Wiener index. So you take the geodesic distance, you make the summation over all the pairs, it will give you a number, which we call Wiener index, or sometimes it's called total distance. Okay, we have this. Now, if you make the summation of the resistances, you will get what we call the Kirchhoff index, which is, well, what is funny is that this Kirchhoff index maybe is directly usually computed by the eigenvalues of the Laplacian matrix. I would like to spend time on that, but it's really, I would need 3 hours. And then, of course, we have this random walk index, which is the summation of the expected random walk length between all pairs of nodes. So we do exactly the same thing for the 3 measures. Now, what happens if you make the summation for the whole graph? Well, let's have a look. First, the Kirchhoff index is less than the Wiener index. This is quite expected, and it's less than the random walk index, which is expected as well. If you make summation of numbers which are all smaller, you will get something smaller. No, it's not difficult. Now we have some conjectures. So among graphs with a given number of vertices, the complete graph does minimize the Kirchhoff, it does minimize the Wiener index, and it does minimize random walk. Well, that's great. We have one graph which does minimize everybody. Good. Among all the graphs with a given number of vertices, I'm sorry, it's not the complete graph here, it's the path. I always have one error in my slides. I don't know how to avoid this. Now I found it, so I hope there is no more, but sometimes Okay, so it's the path. The path does maximize all these three. Oh, that's great. So what's next? Well, next, however, if we're talking about this random walk index, things are not so clear. I mean, it is not only minimized by the complete graph, but also by the star. The star is when you have one node which is connected to all the others. And you have the same value for the star and the complete graph in the case of the random walk index. Why? Don't know. Prove it? Well, let's try. We can prove that we have the same value, that's easy. But to prove that it's the minimum value is getting a little more complicated. And it doesn't stop here. If you want to see what does maximize, we said, okay, for the path, it's maximized. It seems to. Actually, we don't have the proof, but it seems to be maximized by the path. Except when you look carefully, you find that actually we have the same value for the cycle. If you take one cycle, you have the same value as the path for the random walk index. So I think that's all from the theoretical things. I will not spend time on the remaining, which is just to play a little. How could I use Is it possible to share here? Normalement, je devrais être correct. Bah, tac, 13 minutes, ok. Ouais.
Ça passe sur l'écran.
Ouais.
Ouais, ça passe aussi en ligne.
Okay. So you have, I said I will talk about AG, so I will still keep a few minutes for that. Now, if you know the software already, you will not be surprised. It really looks like the previous version. If you don't know, of course, I will spend a few minutes to tell you how it works. Well, to try to tell you how it works. Actually, it's not an easy software which does only handle one special thing. There are lots of things, so it's maybe difficult. What is the idea? Well, the idea of this is you propose a problem. AGX does the optimization, so we try to find the graphs which minimize or maximize functions. Eventually, in the case of AGX3, you can use more than one objective, so it does handle multi-objective. And of course, as I said, you can optimize one value per graph, but also one value per node. It looks like a slice extension. It's not so simple. There are cases where you could have some nodes which do not respect some constraints, but some other nodes are actually the best possible solution. So it's getting a little tricky. I mean, one way usually to do Pareto optimization, so multi-objective optimization, usually you take one objective that you do maximize or minimize, and the other one you put a constraint. But if you apply this in the context of nodes, it's possible that you have one node which is interesting, but another one do not respect the constraint. And in this case, you will just forget the whole graph. It's not correct. So you have to you need some native multi-objective optimization inside the software. Now, the way it's working, if you look at this place here, you have 4 buttons. One of them, it's the graph. You can see the current graph we are working on. The second one is what I call the whiteboard. So if I click once, I get both of them at the same time, and click twice. I have what I call the whiteboard. Now you just right-click in the whiteboard, and you can add some elements. And this has changed somehow from the last version. So you can add some elements like some invariance, which is a value which is directly computed from the graph. But you also have some operators, like you can add to matrices, you can compute eigenvalues, you can play a lot. You can add some constraints. Don't forget that we are talking about optimization, so maybe we need some constraints. And it could be a good idea to look at this for constraints, because sometimes if you apply constraint in a straightforward way, it will just not work. I'll give you some hints. If you want to bound the maximum degree, say I want maximum degree 4, like chemical graphs. Now suppose you have 2 nodes of degree, say 5. If it does decrease the degree of one of these 2, it will not change the maximum degree. So for AGX, it would say this does not improve. If you do the same for the other node, it will not work either. You need to work on these 2 at the same time in order to decrease the maximum degree. So if you want to bound the maximum degree, the bad idea is to say maximum degree less than or equal to 4. It will just not work. It will not know how to convert. In this case, you have some special constraints, because we have some tricks to handle such things. So you can build some functions like, so I can go to invariant matrix. Then I have lots of matrices which are already implemented. You can look at that, and you can have a list of the whole thing. What should I say if I don't want to spend so much time but still give some idea? Okay, so this is a way to describe a problem. So you have some values, then you can have some operations, and then you can compute. I put an arrow here, which means I want to minimize this value. If the arrow goes up, it would mean I want to maximize it. So what I do, I right-click, and I can select maximize, minimize, or both of them. I have also this tool, which is called report. And what is it? It's, well, it's written as a triangle. Well, that's not the most important. It's something, it will kind of, it's associated to one cell here. And it means that this value will be used for the data analysis afterward. And if you look how it is, it's built like a matrix. Well, in this case, it's just a number. It could be a vector, row, or column, or it could be a matrix as well. And then if you look at settings there, you will see that actually things are getting a little difficult to handle from within the software. It looks obvious like this, but you have to think of it as it's kind of really difficult. So you can have one value for the graph. It's a single value, that's perfect, like the average distance in this case. You can have a vector. A vector, it means that I have a vector, but each entry of this vector is not associated to a special node. It's one vector for the whole graph, like the eigenvalues of the adjacency matrix. Okay, we cannot say the first eigenvalue is associated to node number 1. No, it's one eigenvalue and it's associated to the graph. But you can also have node values, which means you can have a vector, but the first value is one value associated to the first node. The second value is associated to the second node. And if you swap the order of the nodes, you swap the order of the values. So it's different. Now you can have one vector associated to each node. And you can have this. Well, which makes, at the end, it makes a matrix, but each line or each column is associated to a special node. And now, that's the last thing which I have implemented. Each entry of your matrix could be a value associated to a pair of nodes. Okay? So that's what we get. Regarding data analysis, well, I can just. Oh, I'm sorry, I will just come back here. Well, okay. It was not set, so it doesn't know how to handle that. Of course, it's always when I have a presentation that I have a problem. Anyway, I will not waste too much time. So what we had before, we just have some tables, and then we can draw some plots. So you'd say you take two variables for which you decided to build a report, and you can draw one against the other, like lots of things. But then I decided to implement a second tab, which is associated with vertex. Okay, let's take a real problem and have a look. I will take an easy one. Just, okay, start a new problem. Okay, and then I will just ask a vector like centrality, which I want, say, to maximize. And I will take transmission. I can just say in few words, just some measures associated to nodes. Then which we want to maximize as well. C'est bon, Olivier, t'inquiète pas. Je vais gérer la suite, je pense. Ben, merci à toi. So we can take this. For the optimization, I will take smaller values because it should take a little more, a little too much time. So I take, say, 10 nodes. Now I try to run the optimization. So if you look here, it says that I have one processor working, and when you look at this blue line or red line, it's red when we didn't find a realizable solution. But here we don't have any constraints, so it should not be so difficult. And it's blue when you are getting some feasible solutions. Here I want to maximize centrality. What is centrality? I will do it shortly. It's just basically it's the betweenness centrality. So if you know about it from Freeman 77, but anyway, it's just the number of shortest paths which are going through each node. Okay. So I have this was centrality. Transmission is just to take the distance from one node to each of the others, and you make the summation, and you have what we call the transmission of a node. The funny thing is that when you make the summation of all the centralities, the measure I use here, it's slightly different from Freeman, and you make the transmission. If you make the summation of all the graph, you obtain twice the Wiener index in both cases. So it's interesting to study both of the sets. Now, what happens? Okay, I just found some. Okay, let's have a look at the results. So I will just put some reports to make the analysis. So settings, node values. Node value. Okay. Now let's move to this. Of course, I will not have anything here. Now I have to go to the vertex tab, but it's not enabled. Well, we don't see here because we have the window is cut. So I will try to virtually change. Okay. Oh, well, you cannot see, but we can decide to enable that. And then when you look, you have two columns. Instead of having for one graph, you have all the centralities and all the transmission, you just have two columns. And each line corresponds to a node. So if you look, you have number 1, 1, 1, 1, 1. It's because it's associated to the graph number 1, but it's the 10 different nodes of graph number 1. Okay? So this is what we have. Now, since I'm now studying distances, I have a sub-tab. And you can imagine you have node I, node J, and the values that you decide. Of course, some values may not be defined in all the cases. For instance, the centrality and transmission do not necessarily make sense in the context of the graph. The distances could not necessarily make sense in the context of nodes. So some of them are visible or not, depending. And well, okay, you can play to draw. Say, okay, let's go transmission against centrality, and you get some get some graph, some representation. So here, each circle represents a node. And well, it seems that you have a bound here. And now if you double click one node, you will see all the nodes, all the values that you have on the same graph. And this graph, if you want to know what it's about, you will just have to show the graph and you have this graph. Okay. Now I have some questions for you. I will stop sharing. Oh, what's happening there? Okay, I have to share here. Okay. So I have some questions for you. How to represent a value associated to a pair of nodes? I mean, on a graph, if you have one value per node, you can decide that the node is larger or smaller, or you can make it different colors depending. So we can have some ways to visualize. But if I'm interested in a pair, it can get a little tricky on the graph to look at that. What I could do, I can select a pair and eventually highlight the corresponding nodes. But it's still a question. And I have some troubles with that. Then, regarding the optimization, of course, if you are interested in distances, small graphs will always, or most of the time, have border effects. So if you want to study a property nicely, the graph has to be large enough. So what does it mean? It means each evaluation is taking longer time. So if you have a large graph, it will take more time to evaluate this graph. That's obvious, but it's getting critical. So perhaps we will need some heuristics in there. I will have some. So if you are a student, or if you have students interested in some challenges, I can have a lot. We also need more evaluations. So we need a way to decide what to try and what not to try. Do not waste our time trying to evaluate some solution which we have some reason to believe is not good. So we have this. So CPU time is critical. Eventually, maybe we'll need some parallelization. But we have some problems about the memory as well. When you have one value per graph, it's easy. When you have n values per graph, like the number of nodes, what we had before, it's still okay. I mean, the graph on 64 nodes, okay, you have 64 values. For a computer, it's not large. Now, when you look at the pairs, if you have 10 nodes, you have 45 of them. Already it's getting, well, it's not a lot, but it's getting a number. If you have 20 nodes, which is a small graph with regard to distances, you already have 190 pairs. And then if you want to move on to 50 nodes, you have more than 1,000 pairs. So it's getting really, really critical. What to do in this case? We probably have to change the way it's done, actually. Now what is done, I look at all, for instance, for the vertices, I look at all the values, and I treat the graph with all the values at the same time. Perhaps when I will work on pairs, I will have to keep only the interesting pairs, and the others forget them, because it will be too large. Regarding data analysis, we have some problems as well, because we're getting a large number. But the most critical is for the optimization. So if you have some ideas, of course, they are quite welcome. And I will just finish by, I think it's the end, yes. I will just finish by asking you if you have some problems or if you're interested in anything. And it's related to graphs, just tell me. I cannot improve HGX if I don't have challenges. So give me some challenges and, well, we can work together and we can get some results. So I think that's all about I had to say today. So if you have any questions, do not hesitate. Or otherwise, don't know. Now, what I don't know is if some people abroad if they want to ask some questions, I don't know if I can see them. Okay. No, nothing. Nothing from your side? Okay, so thanks a lot. And and see you next time. If you are interested in graphs, don't hesitate. If you want to know where to find my software, it's at www.AutoGraphiX. That's the name, you have it, .ca. Okay, so you get the software here. Except the version you will have is now is 3.4.8. And the one I just presented here was 3.5. Because the 3.4.8, the last previous, doesn't handle the distances because there are so many challenges with distances that I cannot make it available and feel comfortable because I know that it's quite buggy, yet it has lots of features that I have to arrange. So I will keep some time. Also, I will need to write some documentation because it's different from the previous one in some sense. And maybe you know what it means. It means spending hundreds of hours. So I don't know how to find time. Anyway, yeah.
I tried to find the report for that, but it's not open source. It's not, you can't contribute to the
no, it's not open source. Well, I can say about this. The very first version of AGX1 was the one I made during my PhD. So I was the only guy working on it, and it was working well. There was just, I just found one bug in there. It doesn't mean that I'm a perfect programmer, but it just means that I do it in my way with my logic, and it's okay. We decided for the second version, we decided that people would contribute. Namely, we had each year about 10 students, or between 5 and 10 students working on the software. After a few years, it gets 100,000 lines with duplicates many places. And actually, I was not really comfortable to share this software anymore because I was not convinced it was working properly. So I decided to keep the third version closed. So I have the code for this third version, and I'm the only guy with the code. Well, first version, one other person had the code also. But this one, I'm the only guy to have the code and to make change. If you want to contribute, there could be lots of possibilities, except the code itself, which is in the software, I do it. Just because otherwise there are so many risks that we get some inconsistencies. It's really easy to get inconsistencies. Just to give an idea, this one is the number of lines. I think it's the half of those for IGX2. But when you count the capabilities, it's much, much more. So I think it's I would say it's more efficient. So no, I don't open, the source is not open, but you can use it. You can download it, you can use it, you can do what you want. If you have some questions, you can ask me. I can implement features for you. But no, it's not open. Other questions?